Hey guys, in my last video, I explained how UE searches a suitable cell and get downlink synchronization. I also explained how UE decodes broadcast information of the cell during cell search procedure. Today I will explain random access procedure in detail. Here is the breakup of the topics for this video. We will see all the steps and details of the random access procedure. While understanding random access, we will see how SIP2 parameters related to random access are used by UE. We will take an example of preamble collision to understand contention-based random access procedure. We will see what is non-contention-based random access and how it is different from contention-based random access. Let's start now. Basically, purpose of random access procedure is to get uplink synchronization and to get radio resource in uplink direction to send L3 or L2 message. For example, after boot up, UE needs to search some suitable cell and send RACH connection request in uplink to trigger registration process. UE gets all the random access related parameters of the cell by reading SIP2. Here, I have highlighted all the random access related parameters of SIP2 in red. We will go through complete random access process and see importance of each parameter. UE triggers RACH procedure by sending RACH preamble to the E node B on PRACH channel. PRACH means physical random access channel. Here is the general structure of RACH preamble. RACH preamble consists of cyclic prefix and the sequence. RACH preamble can have 4 possible formats. There are 64 preamble sequences available for each cell, and UE generates these 64 preambles for the cell it wants to camp on. But remember, all these 64 preamble sequences are not available for UE. Few preamble sequences are reserved by E node B for non-contention based random access. I will explain later what is the difference between contention and non-contention based random access. SIP2 parameter number of array preamble denotes the total number of preamble available for UE to choose from. So, number of RACH preamble reserved by E node B for non-contention based RACH process is 64 minus number of array preambles. Preamble available to UE are divided into 2 groups, Group A and Group B. Parameter size of array preamble Group A denotes the number of preamble available within Group A. Remaining preamble belong to Group B, so number of preambles in Group B will be number of array preambles minus size of array preamble Group A. Now UE needs to decide the group from which it needs to choose the preamble, Group A or Group B. Group is decided on the basis of size of L3 or L2 message to be sent to E node B. For example, at the time of registration, L3 message RACH connection request is sent to the E node B. If size of RACH connection request is greater than SIP2 parameter message size Group A, preamble will be selected from Group B, else preamble will be selected from Group A. From the selected group, UE randomly chooses a preamble. PRACH sequences are nothing but data of choose sequences. SIP parameters, root sequence index, high-speed flag, and zero correlation zone config are used by UE in the algorithm used for driving PRACH sequences. Here is the table that tells us format and timing of the preamble. SIP2 parameter PRACH config index is mapped to the PRACH configuration index column of this table. So, by reading this SIP2 parameter, UE comes to know about the preamble format and timing. Total 6 PRBs are used by UE to send PRACH preamble. This number is fixed. Parameter PRACH frequency offset of SIP2 tells us mapping of these 6 PRBs in resource grid. For example, if the value of PRACH frequency offset is 10, UE can use 6 PRBs starting from PRB 10 for RACH request. SIP2 parameter preamble initial receive target power tells us the power to be used for first transmission of RACH request. Its value varies from -120 dBm to -90 dBm. SIP2 parameter power ramping step is mainly used when eNodeB is not able to detect the RACH request. In case of some failure, UE will retransmit the RACH request by increasing the power to power ramping step factor. SIP2 parameter preamble transfer max decides this value. It is necessary to have this parameter, otherwise UE may use all its battery if there are constant RACH failures. UE does not send any identifier while sending RACH preamble. eNodeB calculates UE identifier called RARNTI by the timing of preamble transmission. If two different UEs transmit preamble at the same time, eNodeB will drive same RNTI for both UEs. Now let's see what eNodeB does after receiving random access request. eNodeB drives RARNTI from the time slot number in which preamble is received, calculates TCRNTI for this UE. TCRNTI stands for Temporary Cell Radio Network Temporary Identifier. It is used for further communication between UE and eNodeB. Calculates the timing advance which is transmitted to the UE as part of response message. Determine the information that will be used by UE for sending L3 or L2 message. This information is resource blocks to be used for uplink transmission, modulation and coding scheme, hopping flag, power used by UE for POSCH, uplink delay, and CSI field. eNodeB includes all above information in the random access response message and sends this random access response message to the UE. UE receives this message on downlink shared channel. For this purpose, the PDCCH message is addressed by RARNTI for that UE. If RACH preamble is sent at time X, UE should expect RA response to be received within the time gap of duration Y, where value of Y lies between X plus 3 and XA plus RA response window, where RA response window is determined by SIP2 parameter RA response window size. UE saves temporary CRNTI from RA response. UE applies the received timing correction so that UE is synchronized in the uplink direction and can transmit data to the eNodeB. Uplink resource information present in RAR are used to transmit the data to the eNodeB. UE does not have a permanent identity, so it picks a random number as the UE identity. UE includes this random number in the RRC connection request message. Remember, other identities such as MC cannot be used at this stage, because no security is configured till this point. After sending RRC connection request, UE starts the timer T300, which is broadcast in SIP2, and waits for RRC connection setup message. The eNodeB accepts the transmission from the UE and sends RRC connection setup and downlink. This message contains that random number and is addressed by TCRNTI. Random access procedure can be of two types, contention-based and non-contention-based. Let's first discuss contention-based RACH procedure. Remember, preamble sequences are orthogonal to each other, so eNodeB can easily decode preamble sequences for multiple UEs at the same time, provided each UE is using different preamble sequence. But preamble sequences are selected by UEs in random order, so it is quite possible that two UEs choose same preamble sequence and send this preamble sequence to eNodeB at the same time. it leads to possibility of collision. Let's take an example of collision. Let's say two UEs, UEA and UEB, transmit same RACH preamble in uplink at the same time. In this case, certainly there will be a collision. Now, we will understand consequences of this collision. There are two possibilities. There is collision and E node B is not able to decode preamble sent by any UE. In this case, both UEs will run backup timer with some random value and initiate the random procedure again. Second possibility is E node B is able to decode preamble only from UEA. In this case, E node B will send RAR in downlink with RAR NTI for UEA. But interestingly, RAR NTI will be same for both UEs, UEA and UEB, because both UEs have transmitted preamble at the same time. So, although RAR is intended for UEA, both UEs will decode RAR and work on it. Both UEs, UEA and UEB, will acquire the same TCR NTI present in RAR. Note, UEB still does not know that E node B was not able to decode its preamble. Now both UEs will choose some random number as initial identity and send L3 message, say RRC connection request to E node B, and start the timer T300. But E node B will not be able to decode message from UEB, as UEB is using the timing advance value that was intended for UEA. Now E node B will send RRC connection setup in downlink for UEA. Both UEs will decode this message as it is addressed by TCR NTI. E node B will include random number in this message that was sent by UEA. Although both UEs will decode this message, but random number sent by and received by UEB will mismatch. Only at this stage, UEB will come to know that it has lost out to some other UE in contention resolution. Then UEB will start random access process again and from very beginning. Contention-free random access procedure. There are instances when, because of timing restrictions, contentions are not acceptable. Examples of such instances are handover and assumption of downlink traffic. In such cases, dedicated preamble sequences are allocated to UE by E node B. As sequences are allocated by E node B, there are no collisions and no contentions. Hence, RACH procedure is much faster. Till now, we discussed only one case in which random access was needed. That was initial registration after boot up. But there are many instances when random access is needed. These instances are initial access from RRC idle, RRC connection establishment procedure, downlink data download when UE's uplink synchronization status is non-synchronized, data upload when UE's uplink synchronization status is non-synchronized, during handover when uplink synchronization is needed with target cell, for positioning purpose when timing advance is needed for UE's positioning.